Just started. So welcome everybody. Welcome after the long weekend. First of all, sorry for the hardware issues we had on Friday with the Safe Exam browser file and the Safe Exam browser and Moodle, actually the combination of the two. So far, we did not find out what happened. The ICT, our technicians of this university, are trying to figure that out. For me, that means in the future, we won't use the Safe Exam browser because, well, you have to answer the Moodle questions. We are anyways there in a lecture room. It's like an normal, ordinary exam. You're not allowed to cheat. You all know that, but that should work. Now, looking at the results, it was surprising that many of you had really issues understanding and analyzing code. And I think before I start with the lecture today, I want to clarify that still everybody is able to complete this course who submitted so far all assignments, all mandatory assignments. This is important. Originally, as you know, one of the requirements was, let's go to grading. So here we have a grading part. Look, we have the lecture part with 100 points. You have to achieve at least 50 points. Yeah. The lecture will be a Moodle exam. I've started to prepare the exam questions today. Now, at the beginning of the semester, I thought we do the exam here in the lecture room. So therefore, I booked the lecture room. But now I have to book the PC room, the Hilbert. So what I sent around now yesterday was this email where I proposed 3 new dates for the written exam. This is somehow inconvenient for you. I know that. Normally, I don't change dates during the semester, but here I have to resolve that issue. We need a PC room to write the Moodle exam. The Moodle exam has also benefits. You immediately get your results. You have less questions than in our written LaTeX exam. There you would get 15 pages to fill out, and you would really work this 90 minutes on the exam. In the Moodle exam, you can finish it within 20, 30 minutes, and then you simply leave the room. It's different. On the other hand, multiple choice questions are risky. You know that. So it's, yeah, challenging. Now, the 3 proposed dates are, let me write that down. June 27th. You only need to attend one of these exams. 13, 15. Second one is July, so beginning of the vacation period, 4th. Also 13, 15. And then there's always a date in October. And here I aim for the 16th at 10:15. These 2 dates are in the computer room Hilbert. And this one here is in the computer room EZR. EZR is the computer room in the building next to our Center for Digitalization. So some of you have already booked return flights. I got emails like that. Well, no problem. If you're back in October, take this exam in October. It's fine. Who has an issue with the dates, the new dates? Conflict or something? The exam will be limited. The time will be limited to 60 minutes. So it will be a shorter exam. This time, I got instructions from my doctoral students how to set up the exam in Moodle such that you immediately get the results after the time period is over. So this time I said it that the results should be published at 1500. So everybody gets at the same point time the results. Regardless, if you start a little bit later, you have more time, you finish your exam later, in the end, everybody has 60 minutes. If you start 3 minutes later than your colleagues, you will finish your exam 3 minutes later if you really use up all these 60 minutes. So regarding the written exam, are there any questions? Do you think is this a fair solution? Is it a working solution for you? For me, I simply need the big PC room, computer room. Yes. It could be that I need to activate the registration somehow. Let me check that quickly. Because I also got one message today that registration was not possible. So this one, 27th. And it says you can't register. You see it? You should be able to register. And of the registration is the 17th and the exam is on the 27th. So we can change that to the 25th or something. That's no problem for me. This can be 26th. Good point. That was the issue. So second one, we also fixed that one immediately. 5. Here we need, this is, we have the 7th, the 4th, so we make it the 2nd, 3rd. Well, you all know, if you need some assistance, registration, deregistration, send me an email. Now this one. This one is correct. Okay. Yeah, I know what the issue was. The issue was that I changed the date and the location, but I did not update these registration deadlines. So please pick one of the dates. There is no difference in which date you will pick. The Moodle exam will select randomly exam questions out of a catalog. There will be tags for the different categories, fundamentals of machine learning, where I ask you what is supervised learning, unsupervised machine learning, and such things. Yeah. Yes. Yes. Typically, it's balanced. Every multiple choice question is balanced. So for instance, today I created one with 6 answers. 3 of them are correct and 3 are wrong. And then every answer counts 33.3%, either positive or negative. But actually in Moodle, you don't know how many answers are correct or wrong. Could be that it's not balanced in principle. But normally it's fair to have a balanced multiple choice question. If only one counts with plus 100% and all the others have negative points, that would be somehow risky. And it doesn't help. Yes. You don't need a pen. Probably this is because it's written here. Just a pen. Not even a pen is needed. You just need your university ID, but last time we had some issues. Many of you had issues logging in MO Online. In the future, if we prepare Jupyter Hub exams, like the programming exam in the future, we discussed it already at our chair, then we will prepare accounts for you. We don't need a scissor anymore, pair of scissors. We will prepare everything. You get login credentials at the beginning of the exam. You log in, you have a fresh account. You can work with the account, and that's it. You don't need your own logins. But for Moodle, you need your login. And I think we had 2 external accounts, and you're now in Moodle. Should work if you remember your password. No? Okay. Then we will fix that before the next exam. Okay, so this is the written exam thing. Yes. Yeah, exactly. Yes. In principle, yes. The point is it's a combined lecture with exercise. So those who already passed the programming exam, more than 25, exactly, more than 24, that 9 points, you're safe. You can take the written exam multiple times. Those who failed the programming exam, they have a second chance now. And this is important because we had technical issues. There are good reasons for doing that. Now, for the programming exam, the second chance is on June 25. That's a Wednesday. So actually, everybody can take this exam, but you have to be careful. In the university system, your last attempt counts. So this is the programming exam. For this exam, you need your Moodle account. You need to know your logins. We will prepare Jupyter Hub accounts for you. But Moodle is something you need to be prepared and take your ID with you. If we would be very strict, we could send you away without letting you write the exam, without ID. This is also something important. Yes. We have the room for 1.5 hours, and the exam time will be set to 60 minutes. You will have 10 questions to answer. That's it. The exam will be comparable to the past programming exam, but different, for sure different, but the same style. So we will ask you to understand and analyze code. And I think this is a very smart idea because we all know how to use the AI, how to use AI tools for programming. But what you really need to develop is our skills to understand, describe, analyze, and prepare problem description and code. And that's why we do it that way. I know it's tricky, it's different. It's also new. It's new for us, it's new for you. That's the reason why probably 34% failed the program exam. So 34% of the students had less than 25 points. And I looked at the exam questions and also looked at the best achievements. There were a number of students that had more than 40 points. 50 could be achieved in total. Nobody achieved 100%. And then we tried to analyze why. Maybe the questions were not well crafted or something. No, all these candidates that had more than 40% had some other clicks at the wrong place. So this is the tricky thing with multiple choice questions. You're not absolutely certain. You check something that could be correct, but maybe not. And then you lose some points. But whoever is positive on this programming exam really did well, I have to say. And in addition to the assignments that we write here during this course, you learn a lot. And with the bonus points, you get good grades. But on the other hand, you have to deserve your grade for this machine learning course. It's not for granted that you will pass. And this is something that has changed this semester. And in the past, we tried to catch up everybody, even people who never programmed before. But this time, we give you this brief introduction into learning how to program. But if you don't practice programming at home, then you have a hard time in our exams, you see? So for this program exam, you don't need to register. There's nothing in MO Online to do. We'll simply take your ID, come to the computer room, take the exam. If you want to improve your results of the first program exam, feel free to do that. I did that once when I was a student for, it was Messtechnik, so signal processing measurement thing, because I thought I failed. And then I really learned a lot for 3-4 weeks. I think it was during vacation period or something. And then I said, now I'm prepared. Now I will go to this attempt. And I was lucky. I really improved my score, but it was close. And the lecturer said to me, well, you passed. You had a 3. Why are you here? So, well, I thought I'm negative. And now I'm prepared. So it was in the end not a 1, it was a 2. I only slightly improved my score. That's life. Any questions to the grading? This is really important, therefore we take the time. Pardon? I did not get it. Acoustically, I did not get it. What do you mean?
We've already we're already in the lesson 4 of the programming. So will it be included in the exam, programming exam also, or still full lesson?
Assignment. Oh, okay. Well, this question is actually the wrong one, because it does not really matter what algorithm you see. It does not need to be a Gaussian process or a probabilistic time series model. It could be anything else. It could be a path planning algorithm. I will simply ask you, what are the limitations? Will it work for any mobile robot? Something like that. And then you need to answer that. So it's not really directly connected to our assignments. Of course, in the first programming exam, it was connected somehow, because we said, let's add some feature regression, linear regression exam question to it. And you were able to optimize the code, tune the hyperparameters. No, this is also, well, hard to answer. Honestly, my intention is not to create hard task exams. My intention to create questions that are really challenging in such a way that you need to think about it. So lecture part, exercise part. Total 50 points, you need to achieve 25. So if you need to take this second chance programming exam and then you achieve less than 25%, then you have to retake the whole lecture. So this is the drawback about this integrated lecture exercise thing. The benefit is, once you achieve this, so this limit, then you can take these exams and you have time up to 1 year to pass this course. Yeah. So you have 2 more days now for the last submission. And then we want to announce all points that you got on the 20th. That's not written here. Yeah, not written. On the 20th of June, I want to release on Moodle all points that you achieved on the assignments. On the 25th, you would have the second programming exam, and then you know if you can attend the final written exam or not. You might ask, how can I prepare for the written exam? Here, I highly recommend looking at slides is good. Understanding concepts by looking at the script makes sense. And ideally, you were here in the lecture rooms. This really helps. And I'm also happy that many of you are still here at the end of this semester. This is not common. I know that you're very busy. You have a lot of courses to take and many assignments to write and exercises. But studying is a full-time job. It's a tough job. The other thing is, after the completion of this course, you can be really proud that you achieved something. It's not a course where you simply attend and then thank you for the grade. So who did not like the programming exam at all? I have to ask that. Well, you don't need to raise your hands. It's fine. Who did like it as it was created somehow? You also don't need to raise your hands because it's a weird situation. We have the course evaluation anyways. Feel free to leave us your comments there. That's really helpful for us for the next generation of students next year to improve this course. All right. Did I forget anything? I got one email that some of you won't have time in June or July to take the written exam. Well, no problem. I looked at your program assignment you passed. You can write the exam in October or even later on if October is not a good date. There will be multiple dates for the exam during the year. Normally we have about 6 exam dates during the year. But I would understand if you're an Erasmus student, you need to complete the course and you have severe issues, then contact me. All right. Then I stop screen sharing. Now I have to watch the blackboard here. Turn on the light. So what I have prepared is 3 pages where I guide you through the development of this probabilistic time series model. Last week we introduced it really in a short manner. Today I want to go through that step by step. Actually, what I present now is exactly like that written in the script. So you don't miss anything. You can take notes, you don't need to. You have the script, and I will try to follow the notation as close as possible. I might omit some subscripts. Question? No? Yeah. We still have time. We are perfect in time. Okay. If you have other questions after the lecture, I'm still here. I have time today. Or you write me an email. So we talk about the probabilistic time series model. And it's actually a model where we have time, then we have some joint angle, some variable, and we have different demonstrations. Like that. And our goal is actually to compute a model that represents here these demonstrations using a probabilistic distribution. So I indicate this now by some standard deviation and some mean. This is now the mean. Here we have some standard deviation. And our goal is to learn a distribution over some trajectories, which I denote by tau now, and I will introduce it. But this is the game. So we start by defining what is given. Given is some data, d, and here we denote this d by y, 1, 1, and then we have 2, 1, 3, 1, till y, capital T, n. Now capital T are the number of time steps. For instance, here we could say this is capital T is 100 or 1000. So we have a sequence of measurements, and the number of measurements is denoted by capital T. And the second variable is denoted by this lowercase n. And n is the number of demonstrations. Or experiments, measurements, whatever you call that. Typically, we call it demonstrations because in robotics, you could think of different demonstrated solutions. So I wave my hand multiple times. You record my arm trajectory with a Kinect camera or whatever. And then you have n of such demonstrations. And now to conclude, we have this trajectory tau, which is then given by a vector. And we might denote this trajectory by letter j. So j is one of them. This is now j. And again, we have this sequence of measurements. Y capital T j. This is our vector. That's what we like to generate. So in the end, we will now develop this model, and with this model, we can generate such vectors. So it's a trajectory generator. That's what we do. Now, it's a two-step process, the derivation. In the first step, I will define a single time-step model, and that's something that we already know. And then I will extend it to a multi-time-step model. So, so number one is the single time-step model. And in this model, we define this distribution over by lowercase t. So lowercase t is between 1 and capital T. Given some parameter vector w, and you all know we love our Gaussian distributions for good reasons. And I write down now here the single time step model using this feature matrix and our W vector. We have a standard deviation that is denoted by sigma y, and as yt is a scalar, we don't have the identity matrix here in our multivariate Gaussian distribution. So that's the single time step model. Well, this is something that you all know because we already defined these models. Bayesian feature regression, that's it. We only neglected, or we did not use such a time index here. So this feature matrix, Vt, is in our case, let me first define it, a mapping from the one-dimensional space, because Yt is one-dimensional, to an m-dimensional space where m is the number of Gaussians. In our case, if we use exponential basis function, or could be number of model parameters, m, if we use any other feature transformation. Gaussian slash, we call it features. Now, phi t is defined to be an exponential function. And now here it becomes a bit different to what we had. We had this in an exponential function in the past as Gaussian basis function, but now we are introducing a new helper variable, auxiliary variable, denoted by z, and z is now the movement phase. So I have to write it down here. Zt denotes the movement phase. And let me explain why. If you remember, we said, yeah, we tried to model here these trajectories with Gaussian features, but we would like to be independent on the number of time steps t. If it's 10 minutes, 5 minutes, 5 seconds, actually the model should work for any time. And ideally, you want to learn a model once, and then if you can change this time, you can speed up the execution of some movement. You can record a slow motion, and then you can model it. And then you have this tuning knob denoted by movement phase, and you can execute it 10 times faster. Now, in the simplest case, there's a linear mapping between time and this movement phase. Let's denote this by Zt, the y-axis, and this is our time step t, capital T. Sorry, this is capital T. Here we have 100, here we have 1, here we have 0, here we have 1, and in the most simple case, we have a linear mapping between time and the movement phase. So it actually converts our time index to some scalar between 0 and 1. That's it. Now, what's the benefit? The benefit is, if I do that, I can use the same definition of basis functions here. Look at this equation. Regardless if my data that I get has 100 time steps, 200 time steps, whatever. Everything is scaled to 0 and 1, to be between 0 and 1. So this Zt here is between 0 and 1. And I have here a subscript I, and I is one of our m basis functions. So I have to denote that I is between 1 and m. And now I will sketch that. Let me sketch that to make that clear. Perfect. So you can see that. Now let's have a look. Now on the x-axis, I have ZT. ZT is between 0 and 1. And on the y-axis, I have here now our basis function in principle. And now we assume that we can raise some Gaussians here. Let me use different colors to illustrate that in a nice way. Let's assume we have 3 Gaussian basis functions. Each of them has a center that is between 0 and 1. So this is C2, this is C3, and here we have C1. And now you see that we can define this basis function once. We can pre-compute that. Then we can collect data, and we can use this basis function for any type of data because it's normalized to be between 0 and 1. There's another important parameter that is actually this bandwidth parameter called H, or in the past we had the standard deviation for that. There's also a rule of thumb in the literature because you try to define this basis function in such a way that you have enough features, of course, to model the complexity of your problem. So that's something we had in the past. Maybe 5 Gaussian basis functions are fine, or we need 20. So you have to test it. And the other thing is you want to ensure that you have some overlap, but you want to avoid to have a redundant system where 2 Gaussians would explain the same data point. If you have a complete overlap between the 2 Gaussians, your linear regression doesn't know which one to choose if you compute your parameter weights. So for this rule of thumb, this H is typically computed by C of I plus 1 minus Ci divided by some scalar. You find it also in the script. Rule of thumb. You don't care because in the assignment, this is implemented for you. What you care is you need to understand the concept. So, all right, this was the single time step model. Now we move on to the multi-time step model. Now we will exploit some property of our data. We will assume, how did I denote it? That our trajectory tau, given our parameters, is computed assuming a factorization over time steps. So this is here the product symbol. And we compute the product over t is equal to 1 until capital T, so for all t time steps. And then we assume that we can do that with our Gaussian single time step model. Yt and j, what was our trajectory? We had our power parameters. And we are missing our features. Phi t transpose w. Can you read that? That's our feature matrix. Squeezed in a little bit, but you know, phi times w. With that, we can generate our nonlinear trajectory. There's one thing that you might miss. Now that I use this phi again, you're missing one thing. If you have these three Gaussians, well, your phi t matrix is given by the individual phi t's that are concatenated until phi m. This is our single time step model, and we have m features. Element 1, the dimension is 1 times m. And if you look at our equation on top, we are using phi t transpose, so it's actually 1 m times 1. Sorry, m times 1. That's the dimension because we are using the transpose operator. And now in the next step, we will define a feature matrix that has the dimension of capital T times m. And with that, we can model the whole distribution. So assuming that the individual time steps are identically but independently distributed, IID, I can apply the rule of the product of Gaussians, independent Gaussians, and this product of these many Gaussians can be explained by a single multivariate Gaussian distribution. Here we need now our trajectory tau. I will introduce now this feature matrix A as we had it in Bayesian feature regression. This is tau. Today is not my best day for blackboard stuff. Let me make that cleaner. So we model trajectories tau using a feature matrix A times W. And now we have sigma y squared times the identity matrix. That's our model. A is a feature matrix of the dimension T times M. W is our feature vector of the dimension M times 1. and tau is a t-dimensional vector. What we do here is for one-dimensional trajectories, we can extend it to d-dimensional systems, no problem. You find that in the script. You find it also in your assignment, the extension. Here, I assume for simplicity, we have just a one-dimensional temperature measurement, whatever. It's fine. The only thing that changes is how you compute this matrix A. And you would have many more W parameters. So this step, let me introduce here the property that I use. This is really crucial and important. So from here to this step, if you think back what we discussed when we derived Bayesian feature regression, we said the product of two independent Gaussians, let's say random variable A given mu1 and sigma 1 times a Gaussian over random variable B given mu2 and sigma 2. Hope you can all see that, is a multivariate Gaussian distribution where you have a concatenated vector. Remember, A and B are both now in a long vector given mu1, mu2, and then you have a diagonal covariance matrix where you have sigma 1 and sigma 2 in the diagonals, and all other elements are 0. This is the property of the product of independent Gaussians. And if you look at that, here we had the product of two Gaussians. In the top case here, we have the product of capital T Gaussians, but it's still the same. The result is simply a multivariate Gaussian distribution where you have a very long vector with T elements, capital T elements. That's it. And that's why we can derive this model here. And our model is done. This is our model. This is our probabilistic time series model. What you miss, one thing, is matrix A. Well, how do you compute this matrix A? Well, you simply concatenate T feature matrices. That's it. Be careful with the transpose operator that the dimensions match. This is really tricky always. But in the end, you use capital T single time step models. That's it. If you implement it, you always will double check that the dimensions match. In the script, it's correct. Here on the blackboard, I always have to look up the solution. But the idea is clear. Single time step model, assuming IID samples, so product of Gaussians resides in the multivariate Gaussian distribution, and our Gaussian distribution uses a very large feature matrix A. You can plot this feature matrix A in your Jupyter notebook. You can have a look at this feature matrix. And your W parameters, you decide how many Gaussians you want to use. Typically, you say 10 per dimension, and then maybe you have 3 dimensions, X, Y, Z coordinates of Euclidean measurements. Then you would have 30 Gaussians. Yes? Yes. Only the diagonal elements are set because you assume IID. The Gaussians are independent. If they would be dependent, then they would be non-zero. They are non-zero, these covariance elements, if we apply linear regression and we learn this prior distribution from data. So let's discuss that briefly. We are missing two steps. First is how to compute W. And the second step is how to use our model to generate data. These two steps I want to define now. I'll use this one now. So number 3 is the model learning part. So the goal is to compute this W vector given n pj's, where j is 1 to m. So we have these demonstrations. Now, using this demonstration, we want to compute this W. So step 1, for each demonstration, or for each tau j, you compute a wj vector via least square regression, for instance. It makes sense to regularize it. You know the trick. Not y. Tau. Tau j, of course. I'm using now a color to denote the difference to classical feature regression, Bayesian feature regression. So we get this W vector n times. Now in step 2, we compute statistics about it. We compute the mean, 1 divided by m over the sum over all wj vectors. That's the mean. And we can also compute the covariance. And plus 1 and minus 1, sorry. Over j is equal to 1 to n. And here we compute the difference between our computed mean. This is also a vector. We have this vector notation thing times wj minus mu w transpose. And these two things here, mu and sigma, define our distribution over W, which is given by this Gaussian mu w vector and sigma w. There's only one difference to my notation here and the notation in the script. Here I'm conditioning everything on tau or on y. I think I condition it on y in the script. That's the only thing that is different. Which means that we compute that from our data. But in the end, we compute here prior distribution. So to recap, I give you 20 demonstrations. Each of them have 1,000 time steps. You compute once your basis function matrix A in the beginning. Then for these 20 demonstrations, you compute 20 times your W vector. And then you simply compute the mean and the covariance of it. And that defines your prior distribution. And the last step that is now missing is the prediction phase. And that's also something that we already discussed. Let me use that one now. We're good in time, well in time. Three or four? Four. I think it was four now. Number four is predictions. We start with the simpler case. We start with the prediction of the whole trajectory. So, given is our model. This is our model. And our prior. We have also the prior distribution of our model parameters W. Our goal is to given the prior and the model, as mentioned at the beginning, we want to model this distribution P of tau. Well, P of tau is given by the marginal over tau of our model, the posterior, A times W, sigma y squared I, times our prior. And you remember, this is the same equation as in Bayesian feature regression. I think here we never use the subscript. And we integrate over W. Now this marginal, as you remember, can be solved in closed form. So the product of two Gaussians where you integrate over this W parameter can be solved in closed form. So the result is a Gaussian distribution over your trajectory tau given your feature matrix A times your prior mean and now I have to be careful. With the covariance matrix, we have the original data variance plus the transformed covariance of our prior. My mistake. So that's the result. If you have your 20 demonstrations, you learn your model, you compute your prior distribution, then you would like to say, okay, let's execute the mean, compute the mean trajectory. Well, you can use your prior, but these are feature weights. What you want is a vector of numbers. You want to compute this tau. Well, how can you do that? You transform it back into this trajectory space by multiplying the feature matrix A times your vector with the parameters. Mu. In addition, you have a probabilistic model, you get an uncertainty estimate. And this is exactly what I sketched at the beginning, which is gone now. We said we have these different demonstrations and we want to predict this mean and we want to have this uncertainty estimate. That is the result. Now, there's one last thing I need to mention now. Predictions using this model is nice, so you can generate complete trajectories, but this model is way more powerful. You can use conditioning of Gaussian distributions to complete trajectories. I will sketch it, this idea. This is something that you will also apply in the assignment. You will compare to Gaussian processes. And one big benefit of this probabilistic time series model is actually that you really can complete data. It's actually 4B is conditioning. So what does conditioning mean? In conditioning, you have here your trajectory tau or y, whatever. Here we have time. And you know, well, this might be your mean model, mu of w given y. You might also have some uncertainty of your model. Let's use the standard deviation. Might be larger at some areas because the demonstrations that you had, it's always symmetric. That's important. Yeah. So this is your model prior. Now in conditioning, you get some observations. Let's say these points, these 3 points. Typically, I say these 3 points can be modeled by some vector O, O1, O2, O3. These are observations. So in conditioning, you condition on explaining these observations. So you want to generate a trajectory tau that exactly passes through these observations, as in Gaussian processes. But you also want to use the prior to generate the trajectory itself. So what you will generate in the end is some example that passes through your observations and will recover the shape of your prior. If you would get different observations, you get a different trajectory. You will play around with that in the assignment, but I want to show you the equation. As a last thing, I don't want to write it down now. I want to show it to you. I'm using a script. So here we have the conditioning part. For each of the observations that we observe, we compute a vector O. And this vector O is used to generate a prior distribution that explains our observations here. This prior distribution is called mu of W given O now. So that's the main difference. And the equations that you see here, these are the equations of conditioning. Gaussian conditioning, if you remember the equation. Let me look it up for you. Here we are. So we discussed two properties of multivariate Gaussian distributions. The first one was marginalization, and the second one was conditioning. And the result of conditioning is, if you condition a distribution P of A given B, then the result is the mean of A plus a correction by the contribution of the random variable B. Now looking at the script, we have our prior mean plus a correction by our random variable O. O are the observations. That intuitively makes sense. We have a prior distribution that generates the mean here, this orange line, plus a correction that reflects the importance of passing through our observations. So that's conditioning. And this is a very powerful property. The interesting fact is you can control the importance, how important it is to pass through these observations. You can say, I want to trust my prior, or I want to trust these observations. And the way how you scale that is using the uncertainty. In the assignment, you can play around with this uncertainty estimate. and the importance of passing through these observations. It's actually controlled using, where is it? Sigma O. This parameter scales the importance of passing through your observations. All right, to wrap up. Well, there are, of course, slides for the time series models. But to summarize this thing again, where's my conclusion? The mathematical description of a probabilistic time series model is Bayesian feature regression over time series data. The model itself uses the feature matrix A multiplied by a W parameter. We learn this W parameter through, in the simplest case, linear regression, where you have n demonstrations, you compute the mean of this m, you first compute these n W vectors, then you compute the mean and the covariance of these W vectors. That's your prior. Once you have your prior, you can generate already a basic model. You can generate the mean trajectory by using this prior vector multiplied by your feature matrix, you get your trajectory. You also get the standard deviation, the uncertainty estimate using your prior. What is really powerful is afterwards applying conditioning, where you have some observations and now you can scale the importance of passing through the observations or through trusting your Gaussian prior. And this can be very helpful, especially in robotics. So you might have situations where it's very important to stay close to your prior because the prior is safe. And in some other regions, like where you're not close to humans, the system can be more flexible, can adapt by conditioning on some user inputs. So probabilistic time series models, we did not mention it explicitly. We said, okay, we discuss here a single time step model, then multi-time step model. If we have multiple dimensions, we have a very large vector in our multivariate Gaussian distribution. We model the covariance using our prior distribution. So we capture the correlation between different dimensions in our prior distribution. And I have visualized that. If you remember, we had this figure. What was the visual explanation? Maybe it's at the end. Here it is. If we have multiple dimensions, we put them all together in one long vector, then we compute the mean and the covariance. And what happens is that if we look at the dimensions here, denoted by these blocks, you see that we capture in our model the correlation between the individual dimensions and in time, both things are captured. You know that joint 1 is correlated with joint 2, maybe only at the first 10% of your movement trajectory, maybe later on not. Because time is modeled through this arrangement of Gaussian basis function, where we say, okay, we put some m basis functions between 0 and 1, and with that we model time. And if you have multiple dimensions, you would have d times m Gaussian basis functions, where d is the dimension of your problem. So let's say 30 or 50. And in the end, the result looks like that, where you have here from left to right, you have time. This is the beginning of the movement. This is the end of the movement for dimension 1, and then for dimension 2. With that, you model both things. And this is really powerful because in literature, there are many, many models for time series data, but many of them also have some shortcomings. And the biggest one is that they can't capture the correlation between individual dimensions. Imagine you have a drone that flies in the room and you have these XYZ coordinates, and then you use for each of these coordinates a new model, and they are completely independent. They are trained from only X data, only Y data, only Z coordinates data. Then you completely ignore that these three coordinates are highly correlated because our drone can't fly wherever it wants to fly. In this lecture room, there is an open space, and this restricts the search space. Our model would capture that. Independent models can't capture that. Independent models would be, for instance, polygons. You have independent polygons. For each dimension, let's say a polygon of order 3 or 5, then you have 5 parameters per coordinate, 15 parameters in total. Sounds great, but you do not capture the correlation. In this model, you capture the correlation. And the thing is, whenever you apply conditioning, you can condition on individual dimensions. You can argue, well, what happens if I observe the drone at the beginning of the motion in the left corner of this lecture room, and I only know it for the X coordinate and the Y coordinate. I don't know the height, or I don't want to tell you the height. You can use the model, and the model will tell you, well, on average, the height was 4 meters in that right corner. So the model would predict that. That's it for today. A lot of intuition and a lot of equation. Things will become clearer if you use this model a lot. In the last assignment, you use it a bit. If you would use it a lot in the future, you would become an expert using probabilistic time series models. Thank you for joining. Have a nice week. See you in 1 week. This Friday, there's no exercise. Yeah. And I'm around if you have questions.